Okay, so now what we're gonna do is remember we did kind of an ideal op amp and a a comparator and so on. So that was more an average model because I didn't have my driver. I converted my driver to 1 over the ramp height. So that's the way to do very quick linear circuits and so on. But now I want a real circuit for simulation. And what I want to do here is actually close the loop on real components and be able to create. This is creation of an IC. I'm creating an IC externally right in here. So as I do that, what do I need? Well, look, this is the circuit, remember, and with all the values that we did, and the damping circuit to dampen the Q. So we had all the stuff that you see that are the same values as we used before because we want a consistency. We want to see later as we're going to add on a load here to pulse the load, and then we're going to look at the transient response of a pulse load. So what we did was, if you notice this is the error amp. So this is the error amp. Look at the values. They're the same values that we calculated right here. The same values. But now we're using an LT1213, a real op amp. And there's our reference, 1.25. So you could see there's the scale. This is going to be 5 volts because the gain of this is 1.25 at that point, and it's scaled up 1 plus this over this, which is 4 times 1.25, which we should see an output of 5 volts. And when we run the sim, we're going to probe this, and you're going to see it's 5 volts. Now, this goes into what? A comparator. That's the one side. This is my comparator. I'm using the LT1016. That's my comparator. Now, I find out the comparator is a little strange that I need a little negative voltage. You don't need this for real life, but for sim, this seemed to be an issue with sim, that it's not pulling down to ground when I make this VCC 0 ground. So I just give a little minus 2 volts on here, and you'll see it gives me a nice square wave here. And because it should be, it's a comparator. In other words, when my ramp is higher than the VC, this is positive, this should shoot up and reset my duty cycle. Set it to 0. What sets my duty cycle? The clock. So you see, what is this circuit? Well, I want a ramp here. What does a ramp look like? I want it to start from 0 and ramp up to some VM term. Remember, that's what we replaced this for. We replaced this block with a 1 over VM. And instead of now a 1 over VM, that was the average model. This is the switch model. Okay? So we don't replace it with 1 over VM because we want the switching happening. So what's happening is that we want a ramp here. How do we create a ramp? Well, a ramp is created by a constant current source. We want a constant ramp, a constant current source into a capacitor. Don't worry about the switch. This switch only turns on when the clock hits me. When the clock goes up and pulls back, you can see the clock width is 50 nanoseconds. It goes up and down. It'll discharge that cap down to 0. So it starts at 0. And then what? When it releases, it's an open. And what do we see? We see this constant current going into this cap, and we should see a ramp circuit. And we will see that. We'll see. Now, why don't I put this constant current source right here? Because this is an ideal current source, and you want the parasitic stuff, and it'll act very strangely to a short and an open. It doesn't like the current source to be here directly. So what this is a simple current mirror. You could see that this is tied to here. So there's no current that goes into the gates. So the current goes into the drain, which sets up a VGS here. Well, these are identical. So that VGS will set a VGS. And what determines the current? VGS. So this current will be equal to that current. And that current right now is set at 0.5 milliamps, 500 microamps. Now, we don't want a current C. We don't want to pull down. We want a capacitor. The current has to flow into the capacitor. So we can't put a cap here. It's not going into the capacitor. So we have to build another mirror. This is an NMOS. These are PMOS. So how do you build another mirror? The same way you did this one. Now, the current here replaces like a current here. It looks like a current source going down. Well, again, there's no current here. Therefore, that current comes here through here. That current will equal to this current, which will be the same as that current. Therefore, that sets up another, instead of VGS, it's VSG, you know, because you're going from source to gate. To gate. And that sets up the same VS to G here. This is a PMOS, this is a PMOS, they're the same. You match this pair, and you can buy these as matched pairs and buy these as matched pairs. That's what you definitely want. You want these to be matched, and you want these to be matched. Then you will create a current source coming down. So that same is the same current source coming down as this one. It should be around 0.5. And when we sim, we're going to check it. Now, due to parasitic, it may be a little bit different, but it should be close to 0.5, which is 500 microamps, or 0.5 milliamps. So that will create the ramp. And so when we create the ramp, you see, this will create a circuit where I start my duty cycle here. Now, why do I need a voltage control voltage source here? Because I don't want to use a charge pump. A charge pump takes too much time for right now. We'll know later on, if you want to add a charge pump, we can add a charge pump and drive it. The reason why you need some kind of pump, I can't reference this to ground. This is not ground. This flies up to VN and flies down to minus a diode drop. So I have to have some way to gain this up either through a transformer, an isolated transformer, to put a pulse in here, or a charge pump that would charge pump, and this will be my new ground for the charge pump, and turning this on and off. So what I want here is I just do a voltage control, voltage source, okay, and that voltage control voltage source then will jump, will then isolate this between here and here. So if I have a 5 volts here, I'll have 50 volts here because it's 10 to 1. So I may want to scale that down because I might not want 50 volts on my gate to source. But we'll sim it and we'll see what we get, and then we'll change some stuff. Okay, so we understand that whatever this duty cycle is, it puts the duty cycle across here, which turns on at D, which is DT, which is T on, and then turns off when it's D prime, because when this goes to ground, this will be shorted. So this will turn the FET off. Okay, so we should get a square wave here again, and the square wave should be magnitude Vn, and then down to minus the diode drop. Okay, that square wave will produce then a low pass filter, which will produce the output, and the output voltage then will be D times the input voltage. Okay, so let's just run the sim and we'll see what we get. Okay, so we simmed it out to about 1 millisecond, and let's look at the output voltage. Bingo. Oh, look. Hey, it comes out to close to 5 volts. As we move this along, we could see back in here, you're roughly 4.99. So I lied, it's not exactly 5, but that's about the error. So you can see the error is less than 7 millivolts. It's 6.8 millivolts or so error, which is very nice. So it shows that, like I said, this is scaled up through this over this, which is 3 plus 1, 4 times 1.25, which is 5 volts, and that's what we got. Okay, and so the next thing we want to do is we want to say, okay, so what's the current that looks in here? I want to see the current. So instead of adding the current on a voltage, I don't like to do that. All I do is create another waveform, go up to plot, and just add a plot plane. I make sure I click here so it's gonna view on here, and come back to my circuit, and I want to look at the current. There's my current. See, so ultimately my current is going to be about, dropping down towards 5 amps ultimately. Why 5? Well, it's going to be 5 volts almost here divided by 1 ohm. So it's going to scale down to 5 amps. So eventually this average will be 5 amps. So right now, let's see, because it may not have been all the way through. Let's see, where's my cursor? Let's hit this again. There it is. Let's bring it here. So we're at 5 point something, but you see, if we sim to 2 milliseconds, it'll then start to drop down. So let's do that real quick, and then we'll back it off. You go to sim. You got to go on. You have to be on your waveform here. Go to sim, edit, And instead of 1 millisecond, let's put a time of 2 milliseconds. Okay, and then run it again. So now we'll be out to 2 milliseconds. There's 1. And there's 2 milliseconds. So now you can see, here's the waveform. We could look at the waveform right back in here, and that's number 1 waveform right there. So let's see, let's move. Let's get rid of the second one. We just want the first one. Okay, so now we just have 1. So we could see our average, which is right in the middle, is the 5 amps. So let's open this up so we don't have to do this nonsense. So there it is. There's my cursor. So you could see there's the average right somewhere in here. Oh, I only put 1 point something. So the closer that I am to the GAN, there it is. It's close to the 5 amps. Okay, so you could see that. All right, so we come back to here. We have all the way from. Now, what is this? Look at this. You see this? The current eventually goes to 5 amp. Well, wait a minute. Our current in this inductor shoots up to 22 amps. Well, if we size this inductor for 5 amp, for 10 amps, double the current, we're going to saturate the inductor here. So we have an issue. So what do we need to do to solve this? Well, there's more circuitry we need in here. And at another video, what I'll do is I'll add a soft start here, where the soft start will take over the reset from low duty cycle to high duty cycle. See, right now, we're kind of putting out a large duty cycle, the max duty cycle that I do, because beginning, the output voltage is low, which means this is pinned low and this will be pinned high, which give us maximum duty cycle. We don't want that to be the maximum duty cycle here. We want this to be slow. That's why we're going to have to add a soft start, okay, to get rid of this initial current. Okay, so now let's look at what we have here, because as I said, we want to look at these features in here. What's the current? Make sure that that was a ramp. Make sure we control it here, and it creates the duty cycle. So let's look at that. Okay, so we come over here and we get rid of the scissors by an escape. Okay. Okay, click on here and let's see, do we have a ramp circuit? Well, there it is. There's our ramp circuit. So as you can see, our beautiful ramp circuit coming up. Look at that. It's a constant current source in here. See, into a capacitor. Beautiful ramp circuit. Now what discharges it? The clock. This clock discharges it. So let's look at the clock. Boom, there's the clock. And the width is about 50 nanoseconds. So you could see the clock is discharging it, and then we're ramping up. It's discharging and ramping up. And now we want to see C sub V here. C sub V comes up, and there's my duty cycle. Up, and there's my duty cycle. It's the duty cycle is created here. Well, is that my duty cycle? Well, let's check, because this is the duty cycle coming out. There it is. It comes up because this is set. It goes high, and then it stays high until my ramp exceeds this V sub C. And there it is. Boom, it goes low. So there's my DT, and there's my offset D prime T. Okay, so we see that this was working nice. Now let's bring another waveform up in here. Let's bring another pane. Go down to the min again. Okay, now I want to make sure what current is here. I said it should be a constant current. So let's look at the current in the cap, which is the same as the current through here. So we look at the current, and there it is. It's a constant current. Okay, So there's your constant current. Now I want to vary the current. I can vary the current here, or I can actually do a mismatch in here. I can put two of these in here to be double the current. But this is fine. I've got what I need here to create a ramp height of what I need. If I need a larger ramp height, I just put a larger current here. Okay? Let's get rid of this guy here so we know. All right, what else in the circuit that we want to look at? You can see the drive is the same as the duty cycle, so we can go ahead and do that. Oops, we want to put another pane. We don't want to get rid of that. Okay. By the way, it flips to the bigger size if you have this overlapping. If this overlaps this, when I go to here, it just flips this to the other side. When I go here, or when I do a waveform, it'll take the whole screen. So you know, you want to separate it a little bit so it doesn't take the whole screen. Okay, so what we want to see is from here to here. So to do this, you pick here and hold it down because I want the difference. There it is. So you see that matches up with this duty cycle here. And it should, because that is coming from here, and therefore the differential here is the same as the duty cycle. And this, you could see, is the 10 volts. Okay? Because this output here is 1 volt. So if you look at that output of this duty cycle, it's right here, which is close to 1 volt. So let's get that duty cycle by itself. We could come here. Get rid of that. Get rid of, yeah, that's this guy. We can get rid of that. And there's our duty cycle. Get rid of the ramp. So you can see there's 1 volt. Since this is 10 to 1, that creates this as 10 volts. Okay? So what else do we want to do in here to say, okay, maybe you want to look at the square wave here, and we can do that. Well, we already know it's going to be a square wave, but we can go ahead and take a look at that as well. So that's just this waveform here. And you don't have to go here and hold it with respect to here, because it's always with respect to ground for the node. And there we have it. You could see it's minus when this is on, because it's a diode drop. So it's going to be minus, plus, minus. And it's going to go up to the input voltage, which is 12 volts, right here, 12 volts. So it's going to go up to 12 volts, and there we got it. There's a square wave, there's our low-pass filter, and then we get our output voltage. Okay? So the next thing we want to look at is, okay, this is great, but how about if I put, I want to look at a pulse load on here and see if it's stable. Okay, so we come back to here, so we know, let's open this up here. Now, we know we're pretty stable over here, so we're gonna put a pulse load like right after 1.2 millisecond, and then I'm gonna pulse the load, and I'm gonna see, pull this out. So we're gonna put a pulse load. So we're gonna put another resistor. Let's go ahead and just do a copy. First, let's make this resistor 2 ohms. We'll make that 2. Okay, and then we'll just copy this, do a copy. Okay, and then what I want to do is I want to add a FET. So go ahead and copy this, and we want to rotate it. Okay, and then we're just going ahead and draw it out. Now we'll put a ground here, and we're going to draw a little wire. We're going to put a voltage source, so we can just go ahead and copy one of these. Let's move this over here. I don't want this duplicate, sorry. I want another duplicate. So get rid of that. I just want to move this out of the way here. Okay, so we're going to get another ground. And we're going to tie this together. That's going to create our pulse load. Now we have to change this because we want it to be 0, and then we want it to turn the FET on at 10 volts. So we put 10 volts in here, and then rise time is fine, fall time is fine, but we want to leave this on more than 50 nanoseconds. So we want to leave it on for a lot of time. So you could just put, let's see, let's leave it on for 500 microseconds. Okay, so then our period I want to repeat to be 1 millisecond. Okay, but I want it to start somewhere here. I want it to start, say, at 1.2 when it's kind of stabilized. So I'm going to put, let's make it 1.5, so it's going to be stabilized at 1.5. So 1.5 milliseconds. So that's the initial voltage. I'm sorry, it's the delay. Yeah, 1.5 M. So that'll be 1.5 milliseconds. Okay, so now we have it. So what'll happen is, after 1.5 milliseconds, somewhere here, this is going to turn on, and it's going to be a pulse load. So we're going to see this. And then 1 millisecond later, it's going to turn off. So we got to add this to at least be 5 milliseconds or so we could see the downward and upward. So let's go ahead and do a simulation, control, because we'll do 5 milliseconds. And that should be enough because 1.5, and then we're going to add 1 to the point, which will be 2.5, and then we want it to stable, and you can see it. So we'll go up to 5, and that's fine. Okay, so we're ready. We got the pulse loads, and this should act the same. We should see only this on only after it hits 1.5 milliseconds. There's our 1.5. You see it? There it is. And you can see, there it is. And there's 1 millisecond later, you're going to see the pulse again. And it's happening each time. This is the load pulse over and over again. That's happening. Turning on, turning off, turning on, turning off. So there it is. Perfect. So we have our waveform in here, and we can kind of zoom in on this. Okay, let's just do escape. Okay. So let's expand one of these out. And we could see what's happening here. We don't need this duty cycle. We know what this is. This is that drive. So we'll go here and cut this one out. So, rid of that. Okay, so we want to focus in on one of these, and then we can focus in, bring it back, and focus in on another one. Okay, we want to scale this in here. And we could see, here's the ripple coming in as your normal, and all of a sudden you're hitting a pulse load. And then it's coming down, and it's starting to settle back out again to try to get to a new steady state. The new steady state won't be exactly the same as this one because that's our load regulation. So let's expand this out a little bit more. Okay, and get this pulse to a further place. Okay. Okay, so now you can see. You could see it. This is with this load here, the 2 ohms, and now all of a sudden you get a pulse load. You see how it pulls down? Now, there's a lot of people saying, oh, to make this smaller, all we need to do is increase the bandwidth of the circuit. Absolutely wrong. Absolutely wrong. And I'll say it twice. Why? Because during this pulse load, what do you think this error amp is going to do? This error amp is going to be pinned. Because you drop the voltage here, this is going to be much harder than this, and it's going to pin this to be what? High. To say, give me maximum duty cycle. When you pin this, it's saturated, it's gone. That means there is no loop. So this spike is a function of the ESR dump, because now what are you trying to do? You're trying to go from 5 amps here, this is 2, so 5 volts divided by 2. You're trying to go from 2.5 amps to 5 amps. Well, this inductor is not going to go from 2.5 to 5 amps instantaneously. Faraday's law says LDIDT. I'm going to oppose your change. I'm not going to give you that change right away. You're going to increase this duty cycle, so I'm going to allow this to come back up, but it's going to take a couple of cycles. How much? So where is the additional 2 amps coming from? It can't come from here because this initially is 2.5. Well, guess what? It comes from the capacitor. It dumps it. Hence the dump in this voltage drop initially is basically the current that this has to produce dropped through the ESR. That current is the 2.5 amps times this ESR, and that's that initial voltage. Now, what is this? Well, that's the lag of this trying to come back. So it's going to take a couple of cycles. It finally starts to come back, and now this current starts to come back in the inductor. So let's look at the current in the inductor to show you that. This is just a pulse load happening, but yeah, let's leave that in there. Let's open that up, and we look at the current in this inductor. And lo and behold, just like I said, this is at 2.5 amps, and all of a sudden it's got to get up. Well, it doesn't get up right away. It takes a couple of cycles to go. This delay is being supplied by this cap, so it's sucking that cap, energy from that cap. To make this tighter, we can increase the cap and lower the ESR, and we'd have a less of an overshoot here, undershoot. The same way is an overshoot. We're going to begin at the 5 amps, and then we're going to jump down to the 2.5. Well, guess what? When we jump down and release this to 2.5, where's the other 2.5? You can't put 5 amps here. So what's going to happen is the rest, the 2.5 amps, one 2.5 amps is going to go to here, and the other is going to be dumped into this cap. Hence, plus minus, it increases it. That's why you get a voltage up. And you're going to see that on the other end when we look at that. But now, when does this got to play? When finally this starts to reach this steady state back to where this is again, finally we're going to see the slew rate and error amp start to meet where this error amp starts to take over, and it's the pulse width modulation again. So if you look at the output voltage in here, and you take an average somewhere in here, you can see that's about 5.05 volts. And if you take an average over here, that's about 4.99. The difference is your load regulation. And that you'll see, as we lectured, is the open loop output impedance divided by 1 plus T. And that varies, that will be our output impedance, and then you have to look at that times the 2.5 amps will give you a set voltage that we set to, actually we set this to 5 amps, that's why it was 5 volts at 5 amps, but then when you go to a different current, it scales down because of the drop across the internal output impedance divided by 1 plus T times the current. Okay, so this is pretty cool, so let's look at the other end to show you that it jumps up. So that was the downward end. Let's look at the top end of this. Okay, there it is. So now you see you're at a current of 5 amps, and then you're going to drop that down, but the inductor doesn't drop it very quickly. See, this will, if you look at the current here, it'll drop it very quickly. Let's look at that. Let's open this up and show you. I need to hit an Alt. So to get this current here on this wire, you need to go Alt and click onto it. And there's the current. There's the current in here. So you could see the current dropping immediately from the 5 amps to the 2.5 amps. Boom. But you see the inductor is slow. Okay, the inductor is slow. Okay, so that's what we have here. And again, if you want to improve this, you can double this, half the CSR, and you'll probably get half the drop here. Or a little bit less because you still have an inductor. If you put an inductor here, you got the this is one of the reasons why they use surface mount, because it minimizes the inductor. So if you use axial lead, you're going to have another inductor in here, which is going to be another effect in here, because the current in the inductor is going to be also affected by dumping current and pulling back current, sinking current as well. Okay, well this ends the lecture of this stuff. Of the duty cycle control. This is actually the duty cycle control, meaning that this is the real model now here of a real switcher, and we implemented a chip right in here. That's what's in, pretty much what's on inside every chip, plus protection circuits and all that stuff. And other videos later will add on the soft start. And then we'll add on window comparatives for voltage sensing and current sensing. And as we go on, we get more and more complicated as we go into the other books. So remember, this is only the first book, and it's not the full book. The book contains also taking this design and then going discontinuous and finding out, are we still stable in discontinuous mode. And that's in the book, the first book that is on the switch mode applications. Okay. Well, thank you very much, and I hope you enjoyed this video. Bye.